Hello friends, welcome to our YouTube channel. We have learned that an electrical network is called a two-port network when it comprises of one input port and one output port. We can describe a two-port network in 6 ways. Each method uses a set of 4 parameters. As all the sets of parameters describe the same two-port network, there exist definite relationships between them. Today we shall establish interrelationships between hybrid parameters and the other sets of parameters. Hybrid parameters are widely used in the field of electronics. They are often used to develop small signal model of transistors. They give us directly the current gain, voltage gain, input-output impedances of an amplifier. Let us recall how we have described a two-port network using hybrid parameters. While using hybrid parameters, we consider input port current I1 and output port voltage V2 as independent variables, whereas input port voltage V1 and output port current I2 are considered as dependent variables. To express V1 and I2 in terms of V2 and I1, the linear equations used are V1 equals to H11I1 plus H12V2 and I2 equals to H21I1 plus H22V2. These two equations may be written in matrix form as follows. Matrix of V1 I2 equals to matrix of H11, H12, H21, H22 into matrix of I1 V2. The elements H11, H12, H21, H22 are known as H parameters. They have mixed type dimension, that is why they are called hybrid parameters. Some of them are determined by open circuit test and some of them are measured by short circuit test. Now let us first establish interrelationships between hybrid parameters and Z parameters. When we describe our two-port network using Z parameters, we express the port voltages V1 and V2 in terms of port currents I1 and I2. The linear equations used in this case are V1 equals to Z11I1 plus Z12I2 and V2 equals to Z21I1 plus Z22I2. By rearranging the second equation, we get I2 equals to minus Z21 by Z22 times I1 plus 1 upon Z22 times V2. By using this expression in equation number 1, we get V1 equals to Z11I1 plus Z12 times minus Z21 by Z22 times I1 plus 1 upon Z22 times V2. By rearranging this equation, we can write V1 equals to Z11 Z22 minus Z12 Z21 by Z22 times I1 plus Z12 by Z22 times V2. When we describe our two-port network using hybrid parameters, the linear equations used are V1 equals to H11I1 plus H12V2 and I2 equals to H21I1 plus H22V2. Comparing the expressions of V1, we get H11 equals to delta Z by Z22, where delta Z equals to Z11 Z22 minus Z12 Z21, and H12 equals to Z12 by Z22. Now comparing the expressions of I2, we get H21 equals to minus Z21 by Z22 and H22 equals to 1 upon Z22. Now we have expressed hybrid parameters in terms of Z parameters. Let us now establish interrelationships between hybrid parameters and short circuit admittance parameters, that is Y parameters. When we describe our two-port network using Y parameters, we express the port currents I1 and I2 in terms of port voltages V1 and V2. The linear equations used in this case are I1 equals to Y11 V1 plus Y12 V2 and I2 equals to Y21 V1 plus Y22 V2. Now, by rearranging the equation number 1, we get V1 equals to 1 upon Y11 times I1 minus Y12 by Y11 times V2. Using this expression in equation number 2, we get I2 equals to Y21 into 1 upon Y11 times I1 minus Y12 by Y11 times V2 plus Y22 times V2. By rearranging this equation, we get I2 equals to Y21 by Y11 times I1 plus Y11 Y22 minus Y12 Y21 divided by Y11 times V2. When we describe our two-port network using hybrid parameters, the linear equations used are V1 equals to H11 I1 plus H12 V2 and I2 equals to H21 I1 plus H22 V2. Comparing the expressions of V1, we get H11 equals to 1 upon Y11 and H12 equals to minus Y12 by Y11. Now, comparing the expressions of I2, we get H21 equals to Y21 by Y11 and H22 equals to delta Y divided by Y11, where delta Y equals to Y11 Y22 minus Y12 Y21. Now, we have expressed H parameters in terms of Y parameters. Now, let us establish interrelationships between hybrid parameters and transmission parameters. When we describe our two-port network using transmission parameters, we express the input port variables V1 and I1 in terms of output port variables V2 and I2. The linear equations used in this case are V1 equals to AV2 minus BI2 and I1 equals to CV2 minus DI2. By rearranging the equation number 2, we get I2 equals to minus 1 upon d times I1 plus c by d times V2. Using this expression in equation number 1, we can write V1 equals to AV2 minus B into minus 1 upon d times I1 plus c by d times V2. Rearranging this equation, we get V1 equals to B by d times I1 plus AD minus BC divided by d times V2. When we describe a two-port network using hybrid parameters, the linear equations used are V1 equals to H11 I1 plus H12 V2 and I2 equals to H21 I1 plus H22 V2. Comparing the expressions of V1, we get H11 equals to B by D and H12 equals to delta T by D, where delta T equals to AD minus BC. Comparing the expressions of I2, we get H21 equals to minus 1 upon D and H22 equals to C by D. Now we have expressed H parameters in terms of transmission parameters. Now let us derive the interrelationships between hybrid parameters and inverse transmission parameters, or simply called TDash parameters. When we describe a two-port network using TDash parameters, we express the output port variables V2 and I2 in terms of input port variables V1 and I1. The linear equations used in this case are V2 equals to A dash V1 minus B dash I1 and I2 equals to C dash V1 minus D dash I1. By rearranging the first equation, we get V1 equals to B dash by A dash times I1 plus 1 upon A dash times V2. By using this expression in equation number 2, we get I2 equals to C dash into B dash by A dash times I1 plus 1 upon A dash times V2 minus D dash times I1. By rearranging this equation, we can write I2 equals to B dash C dash minus A dash D dash divided by A dash times I1 plus C dash by A dash times V2. When we describe a two-port network using hybrid parameters, the linear equations used are V1 equals to H11 I1 plus H12 V2 and I2 equals to H21 I1 plus H22 V2. Comparing the expressions of V1, we get H11 equals to B dash by A dash and H12 equals to 1 upon A dash. By comparing the expressions of I2, we get H21 equals to minus delta T dash by A dash, where delta T dash equals to A dash D dash minus B dash C dash and H22 equals to C dash by A dash. Now we have derived expressions of H parameters in terms of T dash parameters. Now let us derive interrelationships between hybrid parameters and inverse hybrid parameters, or simply called G parameters. When we describe a two-port network using G parameters, we express input port current I1 and output port voltage V2 in terms of input port voltage V1 and output port current I2. The linear equations used in this case are I1 equals to G11 V1 plus G12 I2 and V2 equals to G21 V1 plus G22 I2. These two linear equations may be written in matrix form as follows. Matrix of I1 V2 equals to matrix of G11, G12, G21, G22 into matrix of V1 I2, or matrix of V1 I2 equals to inverse matrix of G11, G12, G21, G22 into matrix of I1 V2. Or we can write matrix of V1 I2 equals to 1 upon delta G into matrix of G22 minus G12 minus G21, G11 into matrix of I1 V2, where delta G equals to G11, G22 minus G12, G21. When we describe a two-port network using hybrid parameters, the linear equations used may be written in matrix form as follows. Matrix of V1 I2 equals to matrix of H11, H12, H21, H22 into matrix of I1 V2. Comparing these two sets of equations, we get H11 equals to G22 by delta G, H12 equals to minus G12 by delta G, H21 equals to minus G21 by delta G, H22 equals to G11 by delta G. Now we have obtained expressions for hybrid parameters in terms of G parameters. Now let us solve a couple of numerical problems to have hands-on practice on implementation of the interrelationships we have developed so far. In this problem, the Z parameters for a two-port network are given as Z11 equals to 6 ohm, Z12 equals to 2 ohm, Z21 equals to 2 ohm, Z22 equals to 6 ohm. We have to determine hybrid parameters using interrelationships. We know for Z parameters, delta Z equals to Z11, Z22 minus Z12, Z21. Putting the values, we get delta Z equals to 6 into 6 minus 2 into 2, that is equal to 32. Now let us use the interrelationships. H11 equals to delta Z by Z22, that is equal to 32 by 6, that is equal to 16 by 3 ohm. H12 equals to Z12 by Z22, that is equal to 2 by 6, that is equal to 1/3. H21 equals to minus Z21 by Z22, that is equal to minus 2 by 6, that is equal to minus 1/3. H22 equals to 1 upon Z22, that is equal to 1 upon 6 mho. In this problem, the G parameters for a two-port network are given as G11 equals to 1 by 4 mho, G12 equals to minus 3 by 4, G21 equals to 3 by 4, and G22 equals to 11 by 4 ohm. We have to determine hybrid parameters using interrelationships. We know for G parameters, delta G equals to G11, G22 minus G12, G21. By putting the values we get delta G equals to 5 by 4. Now let us use the interrelationships to find hybrid parameters. H11 equals to G22 by delta G, that is equal to 11 by 4 divided by 5 by 4, that is equal to 11 by 5 ohm. H12 equals to minus G12 by delta G, that is equal to minus of minus 3 by 4 divided by 5 by 4, that is equal to 3 by 5. H21 equals to minus G21 by delta G, that is equal to minus 3 by 4 divided by 5 by 4, that is equal to minus 3 by 5. H22 equals to G11 by delta G, that is equal to 1 by 4 divided by 5 by 4, that is equal to 1 by 5 mho. So today we have learned how to establish relationships between hybrid parameters and the other sets of parameters. With the help of these interrelationships, we can easily find hybrid parameters when we have another set of parameters readily available. Finally, we have solved a couple of numerical problems to have hands-on practice to implement these interrelationships. So that's all I have for you today. Hope this lecture has been useful for you. If you have any question or suggestion, please drop it in the comment section below. If you have liked this video, give it a thumbs up and share it with your friends. Thank you.